Hello everyone, and welcome to part 2 of our Navmesh to VR tutorial series. I wasn't actually planning on doing it this quickly after the first one, but well, we had a day off today, and I figured might as well do this next part because it should be relatively quick and easy to get through this. First of all, you see that our scene is rendering properly now on. As far as lighting is concerned, it turns out there's a bug somewhere that I haven't really figured out yet what's causing it, related to the to casting shadows. So I've simply turned the shadows off on our directional light just for the time being until I sort that out, because that's not really relevant to what we're doing in these videos. Okay, so the topic of this video is going to be lens distortion. And for that, I'm quickly just going to switch over to Wikipedia, which has a nice little page on distortion that I will copy into the description of this video. And it gives you some background information about the whole lens distortion story in much more detail than I'll ever be able to effectively communicate. But in a nutshell, because we are using lenses in our head-mounted device that magnify the image that is on our display to get a higher field of view, those lenses distort the image. And that distortion is called the pincushion distortion. The further out you go, the more it kind of stretches everything out in into these sort of I'm not quite sure how to call that. And what we need to do to correct that is actually do the opposite of that and apply a barrel distortion to our rendered texture, yeah, that will allow us to render things at a higher field of view, and get a much better immersion effect on our head-mounted devices. When we scroll down a little bit, eventually you come to the logic around correction, which is this brilliantly complex little formula that I won't get into how that exactly works. But the interesting thing to note is that this is actually a formula that sort of never-ending. It applies this constant to every level of basically taking the power of 2 of your the radius between, or the distance between the center of the lens and the point that you're looking at. Then it's taking to the power of 4. That applies the second constant to the power of 8, and so on and so forth, which would be quite expensive to do. Now, interestingly enough, if we just take the first 2 constants in that calculation, it gives a good enough approximation for what we're doing, and that's what you see in most of the code that's out there. So yeah. Let's have a closer look at changing the code, and as we go, we'll discuss some more about the implications and the things that we need to look at. Okay, let's open up our stereo camera scene and have a look at our viewports right left first. So we're going to start with our left viewport first and apply the lens distortion to that one. And we do that by creating a material on that. So we're creating a canvas item material, and then we need to create a canvas item shader on that. Now we can also change the shading mode to unshaded, because we just want the output as is. We don't want to apply any other lighting or anything like that to our shader. And we can go and edit our camera. Oh, sorry, our lens distortion shader. We're going to create a version for our left eye, and then copy that and make a few changes for our right eye. Well, I'll just start typing, and hopefully, hopefully we'll get through it pretty quickly. So we're going to start with, well, let's say that this one is our distortion shader for our left eye. And we're going to start with a few uniforms because we need to provide some parameters to this. So the uniforms allow us to eventually set these variables from outside, but for our starting point, we are going to just use the same constants or the same defaults as we have with setting up our actual camera that we did before, which are my iPhone 7 values. So we have our LCD width that we need here. We have our IOD, and here's our first new one, which is the first of those two constants. And I'm setting that to 0.01, and I'm doing the same for the second one, which is a very light distortion, and that is because the head-mounted device that I'm using hardly has any magnification to speak of. So that's a pretty safe default to start with. After which we can start tweaking it if you have a better HMD that has much better lenses. Then we'll talk some more about what those values should be later on in the video. And last but not least, we need our aspect ratio, which is quite important because else we will get some flattening of our lens distortion. And again, I am just defaulting that to the resolution of the viewports on my iPhone. First thing that we need to do is convert our UV, that's our texture coordinate, which normally runs from 0,0 at the top left to 1,1 at our bottom right. We need to convert that UV coordinate, so that's the pixel that we're rendering currently, to a coordinate system which starts at -1 at the top and 1,1 at the bottom. So let's go and do that. The second variable that we're going to need is we need to calculate where our center of our eye is. Now, as I explained in my previous video, it is very important that the eye, your physical eye, is actually nicely on the center of where the center of of what we're rendering is. Now, we've taken care of that with our asymmetric camera frustum. But we need to make sure that we do the same thing in our shader here. So we are going to calculate where that point is, whether that's probably around there for our left eye and around there for our right eye. And we simply do that as such. Oh, I need to learn how to type, I think. Now, obviously, that offset only needs to apply on the horizontal axis. The vertical axis, generally speaking, the LCD panels will be nicely centered. But there are one or two HMDs where that's not the case, but I'm not going to worry too much about that today. And finally, we want to have actually offset of the coordinate that we're rendering in relation to our center, so that we get a vector from the center of our screen, the place where our eye is centered, to the place that we are rendering. So let's say that we render that pixel, we now have a vector that that points from the center of the eye to that pixel that we're rendering, and that is the vector that we need to start scaling up. We do need to change our offset based on our aspect ratio by simply dividing it, so that we do get an accurate calculation here. And we'll obviously undo that later on. Now we need a square root of our offsets. so that we can get to our radius. Now, interestingly enough, we need the radius squared. So there's no point in taking the square root of this to get the radius and then apply the square to that again to get back to our value. So we can skip a step here. So our radius squared is going to be our offset squared x plus our offset squared y, and that is the one that we need for our, why is that not, oh, why is that not happy? Invalid initializer for variable radius askew. Well, let's see if that goes away in a second. Because that's a floating point, not a vector. Apologies for that. That one is the one that we're going to be applying to our K1 constant. And for those who were paying attention when we were looking at our Wikipedia page, we also need the radius to the power 4. So we can simply calculate that from our radius squared. And then finally, we're going to distortion. We're going to get our scale, which is that nice little calculation that we found. There we go. And now we can simply scale up our offset by our distortion scale. And that's as simple as it is. So obviously we need to reapply our aspect ratio to our offset. There we go. And now we can find our final coordinates. So we take our chords, and that becomes our offset plus our eye center. And this is maybe a little wasteful. There might be a better way to do this. I'm not sure. But I'm just going to check whether we're out of bounds. Now, I can obviously clamp it, but I actually want to make sure that we see where the edge of our image lies. So we'll just do it this way. So if we're out of bounds, we are going to set our output color to black. And why is it still complaining? Probably because we haven't done that yet. And if we are inside of bounds, we first, of course, have to turn our coordinates back to something that we can actually use as texture map coordinates by doing the opposite of what we did before and converting it back to a range of 0 to 1. And there we go. We can go and apply our texture. Look up our texture in our little viewport texture, and there we go. That, in theory, should do the trick. Let's have a look how far off we are. Haha! Look at that. Our left eye now has a nice, well, distortion to it, and our right eye obviously is still the way that it was before. So we can just copy, oops, that was the wrong button. We can copy our code and create our own little shader here. Now I could link both left and right sprite to the same shader and toggle between the left and right eye. That might work. I had problems with that, so I didn't do it that way. I just simply copied it, and then obviously, flip that around to get the correct offset, and now we have both eyes distorting properly. We're not done yet. We now have our materials set up, and we can see our uniforms repeated over here. We actually want to start setting those uniforms in code so that we have some more control over it. So let's go and do that, shall we? So obviously we are going to start by adding in the other variables that we need. Let's actually put a few little comments in here. Distortion. So again, we're going to repeat our K1, and we are going to repeat our K2 there. We already have our new and far plane, and then a world scale. Our helper variables, that's all fine. We can leave that alone. But we now need to go and copy our settings into our shaders. So we're just going to do that as part of our update camera logic. We're going to simply start by saying left sprite dot get material to get access to our material, set shader RAM, and then we go and start with our LCD width, which obviously we're going to set to our LCD width. Let's make our life easier and copy that a few times. We need to have our IOD. Oops. IOD. We want a K1 and our K2. And finally, we also need our aspect ratio, but we're going to do that down here in our resize function, because that's where we have access to that. So that's going to be aspect ratio, which is simply going to be target size dot x divided by target size dot y. And now we just need to duplicate that for our other eye. There we go, and these four, likely they are the same. Come on. So that should still give us the same output. Okay, that was a little embarrassing. It crashed on me. I made two small mistakes. The first was I put the defaults for K2 to 0.02, but the other thing is not realizing that obviously my aspect ratio is set to my iPhone and not to actually the resolution of the screen here. Obviously, whenever you've got these export variables and you change them, you have to be aware that they have now been exported over here, and therefore these are now leading. And in our case, because we're now using our scene in our Navmesh scene, it is actually these variables over here that are leading. So let's run that again, and we can see that we do have some distortion on our lens. And like I said, 0.01 constants are quite light because it's a simple headset that I have. So let's play around with these a little bit more and start with a couple of settings that might be more useful. Starting with 0.22, which should be the settings for gear viewer. And now you suddenly see that not only is our image quite distorted, it's also quite a lot smaller. Now, this is because obviously our lens distortion now accounts for the image being scaled and the image being zoomed by the lens. But we're still rendering our image as if it's not distorted, as if it's not zoomed in. And this is actually the correct representation of our default field of view and what we're currently rendering. But as a result of our scaling, as a result of our distortion, we have all this space around the lenses that is now black, that isn't being rendered, because that field falls outside of that field of view. But we could plop this into our headset, and it would really look really nice, but we would have a very limited, still a very limited experience. So the next step is to actually fill that void a little bit. Now, one thing that I've currently not yet researched is calculating from the K1 and K2 constants, calculating how far we need to upscale our image to figure out how much that zoom factor is. I'm pretty sure there is a calculation for that, and once I find it, I'll add it in. But for now, it's something that I set manually. So let's keep that 0.22 constants and start playing around with that. First thing that we need to do is go to our stereo camera and obviously add support into our shaders. And that's actually very simple what we're going to do here, because we're going to keep our coordinate system pretty much the same. We're still going to assume that once we really reach that that value of 1, that we're actually at the field of view boundaries of our normal field of view, and we're simply going to apply a scale at the end, for which obviously I need another uniform, which we are going to default to 1, so that actually nothing gets scaled. Let me just check my cheat sheet for a second. And we're simply going at the end, divide our coordinates by our upscale. And obviously we need to make the same change to the other eye. There we go. Uniform, float, upscale, 0, and chords divided by upscale. That's that. Now I want to do the same as we did over here, is create a upscale export var, which we are then going to go and apply over here. Now there's one more step we need to do, and I'm going to leave that out just for a second. I'm actually first going to go back to our main mesh, where we should have our upscale variable as an export, and I'm actually going to up that to 1.5. And let's see what that does. That went back to 1. It did not save it. There we go. Let's try it again. That's better. So we can see that that's taken in quite a bit more of the image. We can actually up this quite a bit more. And there we go. Now we actually start filling quite a bit of the image there. However, as you can see, our image is actually getting quite cropped here, because we are still rendering our 2 viewports at the original field of view that we started with. So that's the next thing that we need to fix. Oh, come on. Excuse me. Now, important here is that it's always important to realize that our IOD results in our eyes not being in the center of the screen, and that means that we can't just apply the upscale to our variables here directly. We actually need to offset them by equal measure. So let's calculate what we need to do. So for our F3 we actually can. We can just multiply that by our upscale. No semicolon there. But for our horizontal plane, we actually need to calculate how much we need to add to each side by a simple calculation. And now we can add that to both. There we go. And now we actually get both our eyes rendered properly at the right field of view. Well, I say rendered properly, but this is looking very blurry and very icky. And the reason for that is that I am actually warping this image, and it's obviously scaled quite up in the center as our lens gets distorted, while at the edges it's actually getting near where it should be. And that's because our viewports themselves are still being rendered at the original resolution at which we started, and that causes that whole stretching of the buffers. Now the solution that we would have there is that we could actually upscale our two viewports to increase the resolution at which we render. And we would simply need to multiply this by the upscale. And then obviously we need to make sure that, that our sprites are adjusted accordingly as well, because they all use factor 2, because we've got our X and our Y scale. However, there is a problem with what I'm doing right now, as we will see in a second. Ouch, what happened there? Now, you can see that the top part of our screen looks a lot sharper and better, because that is being rendered properly. But the bottom part of our screen has gone all weird. And the reason for this is a bug in Godot 2, or a limitation in Godot 2, which has been solved in Godot 3. So the change that I just made would work in Godot 3, which limits the size of the viewport to the size of your main window. Now, because we have already got half our size because of our two eyes, doubling the size or doubling the width of our viewport isn't a problem. But doubling the height of our viewport, obviously, yeah, that is going a little bit wrong. Now we can get a best of, well, sort of like an intermediate thing, knowing that that is the case, so that it's very unlikely that that we would ever put our upscale higher than 2. We'd just be having way too much overhead in rendering. Is that we only apply that part to our width and not to our height. So that means that we need to change our logic a little bit more and only upscale our X and keep our target size Y the same. There we go. I hope I've got the right brackets. And then obviously we do not scale our Y. And there we go. So we do have our resolution in the X direction. We're lacking some resolution in our Y direction, but we can live with that, especially seeing that we probably can tone down our upscale a little bit and make better use of it. Remember, again, we are rendering this on screen. The resolution that we're dealing with, or the aspect ratio of the screen that we're dealing with on the LCD is probably slightly more like this. Oh, that's not. No, that's adjusting quite nicely. But as you can see, now our upscale is quite a little bit overdone. So it's really playing around with it a little bit and to make sure we get the right values there. So just try this a little bit, and that's looking better already. There's one more thing that I want to add in here right now, and that is simply a little divider line here as a guide to make sure that you insert your headset correctly. So yeah, let's try that. Okay, I have just copied in this little white dot PNG file into this project, which is just a 1x1 pixel white dot, as simple as that. And we are simply going to add that in as a sprite. There we go. So there's a little sprite. We're just going to set our texture of our sprite to white dots. And as always, I am just going to position that very simply, oops, like this, so that we can see what our end result is. Obviously turn centered off, and as you can see, we now have, oops, a nice little white line going down the middle of the screen. Obviously, we need to make sure that actually gets positioned where we want it to be. So let's do our same old. And for this one, I'm not going to, well, actually I might as well. Divider. Let's actually rename that one. Let's be consistent. There we go. And that is now simply a matter of setting our position to target size. I really am not typing very well today. And divider dot set scale. 2.0, we make that, that's right. Size.y, there we go. And that should now result in that nice little line dividing our two screens at the right position. Perfect. All right, the last little thing that I wanted to look at in this video before we're done for today is just show everybody this little website that I found, which is a profile generator for Google Cardboard. And the nice thing about this site is that it first of all gives you some detail about the setup of Google Cardboard and basically the setup of most HMDs, actually really any HMD. But also talks about this QR code that you can generate out of this, that you will find on many of the viewers. When you look at this, and this is something that someone else set up a little while ago. So this is for a Gear VR with Note 5. So it shows you the screen to lens distance, which is very close to that 4 centimeters that we had. In this case, the inter-lens distance is 60, so I guess that the Gear VR takes a bit more of a conservative approach than the 65 millimeters or 6.5 centimeter value that I've been using. Here you can see an example where the screen is actually bottom aligned instead of center aligned. The tray to lens center distance is basically the height to the center of your lens. So while we use this to calculate it in the horizontal plane, you can use that for your vertical plane. And there finally are two K1 and K2 constances that we want. And all these settings together, they generate this this nice little URL that you can turn into that little QR code that you see over here, which is using a short version of that URL. Now the downside of it is that if you do scan one of these QR codes, if you have one of those on your headset, it will resolve that URL and it will go straight through to the Google Cardboard site instead of allowing you to see that value right away, which is a bit of a shame. But with a bit of creativity, you can retrieve that whole code, and you can actually paste that into this website. And the moment that you paste that in, you'll see all this this information come up, and you can actually use that to use the correct values and set up your game correctly. Now, obviously, I'm falling short right now in my tutorial series in actually having a setup page in the application. We might do that at the tail end of this, where we'll allow a user to configure these parameters and tweak them. But for now, for our goals, you can tweak them to your own setup for development purposes and for trial demo purposes. So yeah, that was it for today. The next video, I'm not quite sure when I'll get to it. I'm back to work tomorrow, so hopefully I'll find some time over the weekend to prepare the next one, and we'll start talking about actually looking around by using the sensors that are in most of the phones that you can buy today. So till next time.